Okay, the last thing I'm going to talk about for chapter 21 is redox reactions. And I'm not going to go into these too much. I just want you to understand what a redox reaction is and how it happens. So changes in redox, as you probably know, are changes in it's an electron transfer. So with metal ions, it's electron transfer from one metal to the other. And there are two possible mechanisms that this goes through. There is an inner sphere mechanism that involves atom transfer. And then there's also an outer sphere, which is called electron tunneling. So I'm going to kind of draw the cartoons of the two things happening. In the first example, I'm going to just use an octahedral ruthenium. I'll draw, so this is ruthenium 3 bound to a chloride. And then I have another metal ion next to it, which is chromium hexaaqua. But I'm not going to draw all the ligands. I'm just going to draw the important ones. So this would be chromium 2. For an inner sphere reaction, you have to have a bridging ligand. And so what happens in this case is the water is going to leave and be replaced by the chlorine on the ruthenium. So this is for an inner sphere reaction. So I actually make a complex where there's a bridging ligand between the two metal ions. And it's in this bridged complex where the oxidation states change. And on the other side, I end up with the chlorine being transferred to the chromium. And let's just say water goes back in there and replaces that chlorine. Now the ruthenium is a +2, so it has gained an electron. And it gained that electron from the chromium atom, or from the chromium ion. The chromium ion is now bound to the chlorine. What's that? Yes, it is. Chromium +3. So the chromium lost an electron, the ruthenium gained the electron from the chromium, and it was transferred through the bridging chlorine ligands. So this is an inner sphere mechanism, and it involves the atom transfer. So inner sphere literally means that it happens through the inner sphere of each of the metal ions. So that means that the ligands have to be bound, like there has to be a bridging ligand bound to each metal ion. The second, and so these are really easy to recognize. So if I gave you an equation that looked like this, so this is just the long version of the condensed structural formulas, condensed formulas of what I just showed you. Okay, so if I gave you that equation and said, what is this? Is this a redox equation? The first thing you need to do is figure out what your oxidation states are. So because chlorine here is a negatively charged ligand, this is a +3. Chromium over here is bound to neutral ligand, so it's +2. Over here, ruthenium is bound to all neutral ligands, so it's a +2. And over here, chromium now has chlorine, so it's a 3. So you can tell that this is a redox reaction because the oxidation states of the metals have changed. And you can tell that it's an inner sphere reaction because the chlorine has been transferred from the ruthenium to the chromium. Outer sphere reactions happen through electron tunneling. So I could draw the same reaction up here, except I would never have the metals bound through a bridging ligand. So if I had something like M2 plus something with a 3 plus metal ion, basically all these guys have to do is come close to each other, and the symmetry, the orbitals, so I'm going to call this L and L. These ligands just have to come close to each other so that their orbitals overlap. And let's just say that there was a p orbital on each one of those ligands that had the correct symmetry to interact. Now you can transfer an electron from one metal ion to the other. This is called an outer sphere complex. And those ligand orbitals overlap to allow electron self-exchange. And then you get the two products with transfer of electrons, but they all retain the ligands that they had originally. This type of electron transfer is defined by something called Marcus theory. Do you guys talk about Marcus theory in physics? No. Okay. So you know potential energy wells, right? So if this was a potential energy well for, let's say, an iron 3 plus with 6 waters around it, and in the iron 3 plus is more stable than iron 2 plus. The electron, basically, if you think about the distance of the atoms from the nucleus, or from the center metal, from here they're very close, and then they get farther away, and same thing here. So at regular like room temperature, you have some vibrations, and you have the atoms and they're vibrating due to thermal vibrations, and they can get up to like this point at a certain temperature. Where these two lines cross over, basically they have the same geometry, or they're similar enough where there's no energy barrier for electron transfer to happen. So there's a bunch of equations that explain this, but basically the equation is setting the potential energy equations of the reactants equal to each other so that an electron transfer can happen. This is called Marcus theory. So electrons can just jump. As long as they're close, they can just literally tunnel through orbitals that are near each other. I think electron transfers are really cool. Proteins are amazing how you can transfer electrons. Like if you have a big bulky proton, you can have a tunnel like straight through the protein from one end to the other, just because of the way that the amino acid residues are arranged, so that the symmetries of the orbitals will overlap the whole way. It's pretty awesome. Anyway, that's the end of the story for this. So there's one last section in chapter 21